And they let you stay here as well, so...
Yeah, that's amazing. Well, up until now. Let's see what happens in the next few weeks. Yeah. But up until now, they even let me come back.
Yeah.
You're listening to The Cosmic Cast.
Hello everyone, and welcome to another Earth and Solar Systems Group Cosmic Cast. You're here with me, the peculiarly perfect Ricky Bahir. On my right is the forever beautiful Dr. John Pernett Fisher.
Hello.
On my left, we have the doe-eyed Tom Harvey.
Hello. Doe-eyed.
And my gosh, do we have a guest for you all today? May I say, I'm getting emotional. Oh my God. We have the never nefarious and always insidious and self-proclaimed volatile enthusiast, Dr. Romain Tartèse.
Hello.
Hello. And it's actually pronounced Roma, but we're good friends. We're good friends here. How are you doing, Roma?
I'm all right. How are you, Ricky?
I'm very well. It's good to see you. How are you, John?
I'm pretty good, thanks.
Yeah, and Tom?
Yeah, pretty good.
All right, so let's get rocking and rolling then.
All right.
So, Roma, you're obviously originally from France, and I don't know what your parents do, but were they involved in academia in any way?
No, not directly. So my dad works in a high school.
Okay.
So it's not academia, but that's education. And my mum, not at all.
Yeah. So was there any push towards academia, or was it all self-in?
No, my parents were pretty open. So they didn't push me to do it. So, I actually went to academia because I had nothing better to do at that time, and all my mates were going to academia, so I just took part in that adventure as well.
Fair enough. Yeah. So I had a similar, I guess, situation where I just enjoyed what I was doing, and then thought, let's do a PhD. The option became available to me.
Yeah, I think so. I mean, I remember very much during my undergrad, a lot of people were like, I'm done with learning, done with lectures, I want to get a real job. But I never really had that sense, and I always just thought, well, I'll just carry on until I keep enjoying it.
Yeah, I think that is a real stigma with PhDs, though. Also, of the it's not a real job, is it? My parents would always say to me, when are you going to actually start doing work then? I'd be like, I probably work longer days than you guys do, but it's fine.
Yeah. See, I suppose it's a bit different for me because my granddad lectured here in the maths building, and my dad is a geologist, so I kind of followed suit. But
your granddad was in the maths department.
Yeah,
that's cool.
Yeah, but I mean, it wasn't for a lack of love of science or anything. It's just convenient. Got a lot more exposure to rocks because our house is absolutely full of them. Not that that's a complaint.
And so, just brief summary of your journey then. So, where did you go to university to do your PhD?
So, I did to university in Rennes, in Brittany. I started by doing biology for the first couple of years. And in the second year, there was an optional geology module, which I took and loved straight away because we went to the field, had good fun. And then really that's when I really started to enjoy what I was doing in third year, and then did a master still in Rennes. And I followed up with a PhD with the guy I was doing my master with, whom I liked at the time. And and if there is one thing really when you're a student is enjoy what you do, because that's the main, if you enjoy what you do, it should be all right. If you hate it, it becomes more complicated. So I graduated there at the end of 2011. And after that, so my PhD was on granites, geology, geochemistry of granites, very common. And there was a postdoc available at the Open University to look at water in lunar basalt. So I said, well, I can apply and we'll see how it works. And I got the postdoc, so I spent 3 years at the Open University.
So that was originally what brought you over to the UK then?
Yeah, exactly. Yeah.
And was that an easy step for you going, were you in a situation where you were like, I'm just going to take any job that comes my way after my PhD?
No, so it was pretty clear in my mind I wouldn't go in the US, for example. I wanted to stay in Western Europe, let's say. So not too far from France, from friends, from family.
Yeah, fair enough. Yeah.
So, but the UK, Germany, I was looking a bit everywhere. Really. France has got that particularity is that there's really not a lot of postdoc.
Yeah.
So if you want to carry on, you really have
to go elsewhere.
Yeah, to get elsewhere. And across the channel.
And
discover the UK.
And they let you stay here as well. So
yeah, that's amazing. Well, up until now, let's see what happens in the next few weeks.
Yeah.
But up until now, they even let me come back.
Yeah. And you have a tenure position now here as well, don't you? You recently got one, so congratulations for that.
Thank you very much.
Because I think a lot of people do overlook that, how difficult it is to get a permanent position in academia as well. I don't know if it was different back in the day, but now
it takes some time, and it takes some perseverance. So it takes a lot of rejections, basically, and you've got to keep applying and keep applying, and one day you're lucky and you get one.
And on the subject of rejection, I should also say congratulations, because you're getting married in July of this year.
Yeah.
So congratulations.
Thank you very much
as well. And I don't know whether obviously I live in an apartment block, so the post might not be working correctly. But I still haven't received my letter asking me if I want to be the best man or anything. But obviously, it's probably just been put in the wrong box.
Yeah, we're just waiting to see what's happening with Brexit.
We
saw the invitations out after that.
Yeah, fair enough. That's fair. I can agree with that. So that's what originally took you into your volatiles work, then, looking at volatiles.
The postdoc I did at the OU on water in lunar basalts what took me there. So for 3 years, I worked there and started working on big piece of kits, SIMS instruments. So SIMS stands for secondary ion mass spectrometry.
What's that generally used for?
So that's generally used for measuring the chemistry and the isotopic compositions in situ. So we take a polished bit of rock, stick it in the machine, and fire a beam of ions and measure whatever elements we're interested in down the end in the mass spec. And that's the only type of mass spec that allows you to do that for some elements like hydrogen or halogens elements, chlorine, these sorts of things that we were interested in at the time, looking at water in lunar samples.
I think it's fair to say at the time that was quite groundbreaking. I guess there's a period of time where previously no one thought there was going to be that much water to be found in lunar rocks.
Yeah, that was very interesting, because the whole water in the moon thing was pretty much non-existent from the 1970s until late 2008, when 2008 really restarted the whole thing, when colleagues across in the US, Alberto Sal, published a paper where they convincingly showed that they could measure indigenous, so water from the inside of the moon in some samples brought back 50 years ago by the Apollo astronauts. And it really shows that going to some different planetary bodies, bringing samples back and curating them properly, which is what NASA chaps have done at Johnson Space Center, allows you to make discoveries 50 years later, and who knows what we're going to discover on these samples in 50 years time, because lab instrumentations keep improving. It's not that people were not good at the time, it's just they didn't have the capabilities to measure these tiny quantities of water. So that was very exciting at the time, and we did quite a bit of work on the lunar basalts, and cool period.
So but you're still in the volatile region, but you've moved away from the moon. Is that correct, or are you still?
So I'm still interested in the moon, generally speaking, in the geology of the moon, in the petrology of the moon. I'm very excited by the future samples that are going to come back. Hopefully, if all goes well at the end of the year. Our Chinese colleagues plan a sample return mission from the moon, which will be the first one since 1976. And they're going to very exciting areas that has, based on what we think, very young lavas. So the Apollo lavas are between 4 and 3 billion years old, so they're pretty old. Where the Chinese plan to go, it's about 1 to 1.5 billion years old.
So what induced these different lavas then? So there was obviously the older ones were induced by giant impacts that hit the moon, or?
No, it's probably just melting in the mantle, probably due to the decay of radioactive elements.
So that's happened all the way up until 1 billion years.
Well, if it turns out to be true, it's I think, and John can talk about it as well, I think it's quite puzzling, because the moon is pretty small, so to maintain a hot lunar interior such late in the history of the moon, it's
It's challenging.
It's challenging.
And I guess what's different about these younger lavas as well is that there's a significant time gap. All the mare basalts that we see up in the sky when we look up, they all...
So those are the darker areas.
The darker areas,
yeah.
the main bulk of volcanism on the moon, it all took place within quite a well-defined time period, whereas these younger lavas are a bit anomalous. They're several billion years removed from the mare lavas. So it's puzzling indeed.
Yeah, it is. So whether they originate from partial melting of the mantle or from large impacts, but that would be puzzling too, because we don't really think that there was large impacts 1 billion years ago.
Exactly,
but we don't really know. I mean, so bringing some samples back is actually the only way to try and understand what's going on. And it turns out if we so we'll get a piece in the lab, we'll date it. So far the age is estimated based on the numbers of craters we can count on it. And some models about crater production in the solar system. Turns out they may be old. They may be 3 billion years old, in which case it would show that our calibration is completely wrong.
Okay, right. So
either way, it'd be cool.
100%. It'd be very interesting regardless.
So just to finish up on that, I'm not directly working on volatiles and lunar samples anymore, but I'm still really interested in lunar geology, geochemistry, petrology.
Fair enough. So I started to read your paper. Well, I've read your paper, but I'm involved in Martian science.
So you're the one that downloaded it.
Yes, I'm the one person who downloaded it. And then I just printed out loads of times and gave to people saying, it was as though I was making fake copies of your paper.
Slipping side copies of the Metro, things like that.
Yeah, exactly. I saw lots of people using them as like a rolling paper for their cigarettes and stuff. So it's all good. I'm not involved in that side of science. I'm a Martian geomorphologist, so quite a bit of it goes over my head. But, sorry, could you just give us the name of the paper first and what journal it is in? And that's
okay, so
they want to look it up themselves.
The paper we're looking at is just been published in a journal called Geochemica and Cosmochemica Acta. It will go into a special issue, actually, for a guy who died last year, Professor Larry Taylor,
former boss.
University of Tennessee, who's a god in lunar petrology, geochemistry, among other things. And so the paper is called Hydrogen and Chlorine Isotope Characteristics of Indigenous and Late Hydrothermal Fluids on the Differentiated Asteroidal Parent Body of Grave Nunatax 06128.
And for the benefit of YouTube viewers, we'll put a link to that in the description.
And was the long title to make up for a word count? Is that?
No, it's just to impress people. And so these samples are, as you said, they're very interesting for lots of reasons. But one of the main reasons is that they are what we call quite differentiated, quite evolved. So before these samples were found, we actually thought that most crust on asteroids or protoplanets would be basaltic.
So we're looking at early asteroid material.
So we're looking at early asteroid materials. And
sorry, just to clarify, we're talking about meteorite samples. Cool.
So we're talking about 2 meteorites found in 2006 in Antarctica by the US ANSMET meteorite collection program. And 2 actually large meteorites as meteorite go, because it's about 600 grams in total. So these 2 samples have been found next to each other, and they originate from the same parent asteroid. And their chemistry is quite evolved. It's not really like a granite we have on Earth, but it's not far off. And
granites on Earth form in what type of environment?
They form in a whole different types of environment. They can form at subduction zones. They can form by melting of the crust. But it's in between granites and basalts. And so they were really the first bits of a different asteroid that was not basaltic in composition. And so they're very old. We think, so the solar system formed about 4.56 billion years ago, and these samples probably formed a couple of million years after the start of the solar system.
So these so it would be fair to say these represent some failed planet or something that broke up early.
I think so. A small planet. Actually, I say small. We don't really have any constraints. Could be actually pretty big.
I mean, I guess the fact that it's andesitic has to... I guess what's interesting about andesites is that on Earth you tend to associate them with plate tectonics.
You do, yeah.
So I guess that's the interesting question of how do you get an andesitic body?
And I don't think we've got a good answer. There's been quite a few studies on these rocks on how you can form them. In the meteorite world, we've got these differentiated rocks, and we've got the chondrites, which are the non-differentiated rocks.
The starting material for all planets.
Exactly. So bits of dust and the first solids that form in the solar system, and taking different types of chondrites and trying to melt them at different temperature, pressure, amounts of volatiles to reconstruct or to try and form these sorts of materials. But there's no simple answer to that. But these are fundamental in terms of our understanding of what happened in these first few million years of the solar system. Because when we look at rocks on Earth, most of them are fairly young. There's not really any rocks older than 4 billion years. And so looking at asteroids or looking at bits of other planets like the moon, who's not evolved, doesn't have plate tectonics, doesn't have water on the surface, so there is no recycling. So looking at these rocks allow us to try and understand what was going on very early on in the solar system.
So you're interested once again at looking at the volatiles in these samples, and something I got across from your paper is that volatiles were transported to the inner solar system at some point, and that's why we have it on Earth and we see evidence of it on Mars and on the moon. So why and when is it thought that these things happened?
Yeah, that's right. So we think that the inner solar system, when the solar system formed, was probably quite dry, mostly because the temperatures were fairly high. And so the planetary bodies between the Sun and Mars, we think probably accreted or formed without much volatiles, including water. On the other hand, we've got meteorites from asteroids that contains tons of water. Some carbonaceous chondrites contain 5-10% by weight of water. Comets do contain lots of ice. And so that's why we generally believe that water on the Earth, or probably on Mars, was brought by impacting objects such as comets or asteroids.
And so how far into the development of those planets then? So we're talking millions of years after the solar system started to form, our planets started to coalesce together, and then they were dry for a period of time, and then things moved in, or...
That's a very good question, and that's not one that we really have a great answer. I guess for the Earth, what we know, or what we think we know, is there's other types of elements that are called highly siderophile. So highly siderophile elements, when the metallic core of a planet forms, these elements would go into the core. And so we know in the Earth's mantle that the proportion of the different elements are what we call chondritic. So they've got patterns that are the same than in these asteroidal materials. So that can only mean these materials were added after the core formed. Because if they came before the core of the Earth formed, the pattern would be different. So we're probably talking, and so when did the core of the Earth solidify? That's a good question. We're probably talking 50 million years after the formation of the proto-Earth. So you got to think of it as the Earth forms. Probably the last major thing that happened to the Earth is a giant impact that ended up forming the moon. And after that, it's probably when the Earth as we know it starts to evolve. But that's probably at that time, that sort of time, when we think the volatiles might have been added and mixed up inside.
And is that just because there was constant mixing of the solar system, things just flying around during that period? And so I know that there was obviously the late heavy bombardment was that 3.9?
So the late heavy bombardment is much later. If it exists, we're probably talking 3.94 billion years. So the late heavy bombardment was designed after Apollo samples were brought back and where their age were dated in the lab. And most of them return an age of around 3.9 billion years old, which at that point people like Wassenberg and colleagues started talking about the great cataclysm that happened at that time. So it could have happened. It could also
sound like you're not for it.
Well, it's the more and more we look at these samples, and the less and less that spike at 3.9 is prominent. So it might be a sampling bias that the sample collections. So whether the late heavy bombardment is real or not, I think it really comes down to getting more samples and see if it's really a sampling bias or if it's general. But just going back to the volatile, we don't believe that late heavy bombardment had a huge role in bringing in volatiles. The volatile story is probably much earlier. Towards the end of planet formations, when, as you said, there's lots of objects flying around, failed planets, protoplanets, large asteroids, comets, lots of these things.
So how do these samples fit into this picture then?
So these samples, we decided to look at these samples because lots of people have looked at the volatile and water inventory of chondrites, because there's a lot there, but less people have looked at the volatile inventory of differentiated samples like these meteorites. And so these meteorites are interesting because there's actually two things. So when we look at rocks from the moon, Mars, meteorites, generally the only mineral that holds any water in it is a mineral called apatite, which is a calcium phosphate. And the good news is that it's found everywhere, pretty much everywhere in the solar system materials.
Including your own bodies too.
Exactly.
It's what cartilage is made of, isn't it, I think?
Yeah, your teeth as well. Pure hydrated apatite is what our teeth are made of. That's why we have fluorine in our toothpaste, because fluorine can go into the apatite structure. But so these rocks have large apatite, so we decided to look at them like we did for the basalt from the moon. But the difference is that the apatite in these rocks is not actually primary.
So what does that mean? Sorry.
So that means that the rock formed a couple of million years after the solar system. The apatites, they've been dated, so we know when they formed very precisely, and they formed 100 million years after the start of the solar system.
So there's a large gap between.
There is a large gap between, and one of the interpretation is that they formed as a result of impact on that failed planet. And so we looked at the volatile looking at the volatile inventory of these apatites probably don't tell us much about the original volatile inventory of that protoplanet, but of what's happening during shock processes.
As these things are colliding.
But really, what we really need is a much more comprehensive inventory of the volatile inventory of a whole range of bodies, not only chondrites, but lots of these achondrites, because they all participated in creating the planets in the end.
And so when you say it was 100 million years after the fall, that's not actually very early then, is it, in terms of what we know about volatile evolution?
No, that's not very early. That's a long gap. So that protoplanet or that failed planet formed very quickly, for within a couple of million years, and it seems not a lot happened to it for a few tenths of millions of years, and then it got disrupted. Well, it got shocked. Whether it was disrupted at that time, we don't really know. But shock impact processes is the main geological processes acting in the solar system on most bodies. So it's a long time. For us, for geologists, it's a long time after the formation of these objects. It's still very early on compared to the history of the Earth. So relative, I guess, in terms of ages.
So you're talking about like a very diverse range of different types of rocks with different origins, different chemistries. Obviously, in all of those samples, you've got a great elemental range. What is it about the volatiles specifically that makes them so worth researching? Is it just the fact that they're associated in the early solar system, or what is it that they tell you that, like, the heavier elements, for instance, don't?
So I guess my interest in that is the main question we're trying to understand is how and what delivered water and volatiles to the Earth. because as we said earlier, we think the Earth accreted and formed dry. And if we want to understand what are the possible sources, we need to characterize these sources and then compare it to our own Earth. And that question of understanding how and when the water was added to the Earth is also critical to understand why and when life appeared on Earth. Exactly. Yes. So these are the two main questions that drive lots of detailed investigations, detailed/boring investigations in a whole range of bodies. But it'd be good to have a more comprehensive inventory of the diversity that's there in the solar system.
To just go back to it, so the movement that happened at the early solar system to allow volatiles to get to the inner solar system, therefore to allow water to be present, therefore life could start forming. Is that just a normal thing that happens in solar systems? Is everything going crazy at the beginning, things are moving around? Or is it something that's lucky that's happened in our solar system? Because when we look at pictures of other solar systems, they're not normally in the same configuration of ours. Is anything known about that? Or?
That's a good question. That's a question we've been pondering for a long time, whether we're unique, whether it's a combination of unique things that made the Earth as it is and life to evolve on the Earth, or of most solar systems that are like ours. I don't really know. I guess very early on collisions were very common because there's lots of objects flying around in the solar system. I think the recent telescope images, the ALMA telescope, that is now imaged quite a lot of solar systems, show that most of them seem to be quite similar, with a star in the middle and objects circling around. The question whether we're unique or not, it's so far.
You're very unique, right?
Thanks, Ricky. But whether our solar system is unique or not, I don't know.
Tom's not unique, by the way.
Thanks. That means a lot.
I feel like that's the point you were trying to get across there. I just needed to say it.
Is there anything that's not within your field that you find particularly exciting?
Yeah, actually, very recently I got to interact with a couple of astronomers. And I think the constant progress we are making in our field and the constant progress they are making in their field in terms of telescopic observations is bringing ever closer the gap. There's always been a gap between what astronomers look at and what we look at, i.e. rocks. And I think now they are starting to have very good constraints on the chemical compositions of other planetary systems. They have good handling on stuff like the amount of radioactive short-lived elements. And I think bringing that gap together, closing that gap, is what really I find fascinating. And I think the next years to decade, we're going to see some spectacular things working together with astronomers.
I mean, it's starting to get to the point where I guess we're starting to put our solar system in context to other solar systems.
Exactly.
Which is quite a big piece of the puzzle.
And that's pretty cool. And
so Roma, I think we should just wrap it up here and say thank you very much.
Well, no, thank you guys.
You're welcome.
My pleasure.
It's been a good conversation.
Yeah.
And don't forget to check out your new paper in GCA.
Yeah. Do you have a Twitter account that you'd like to plug about? Or
I do have a Twitter account, but I cannot remember my Twitter.
That's really good.
We can stick it in the
that's great. Yeah, we'll stick it in the description though. Thanks to Elliot for doing our DJing today. Yeah, he's making some kind of DJ noises.
You should see their technical setup is quite impressive.
It is actually surprisingly impressive for us, And there will be new episodes every week-ish.
Every 2 weeks.
Every 2 weeks. So listen out for those. And remember to hit the subscribe, the like button if you enjoyed.
And comment.
And please do comment below, And thank you very much once again, Roma.
Thank you, guys.
Hopefully have you on again.
Fun.
Woo!